Welcome back. We're currently working through a little side project here, but really the philosophy of what we're doing, we just created a straight line data set because we know that we've built a model in the past, back in section 01, to fit a straight line data set. And why are we doing this? Well, because the model that we've built so far is not fitting or not working on our circular data set here, on our classification data set. And so, one way to troubleshoot a larger problem is to test out a smaller problem first. So later on, if you're working with a big machine learning data set, you'd probably start with a smaller portion of that data set first. Likewise, with a larger machine learning model, instead of starting with a huge model, you'll start with a small model. So we're taking a step back here to see if our model's going to learn anything at all on a straight line data set so that we can improve it for a non-straight line data set. And there's another hint. Oh, we're going to cover it in a second, I promise you. But let's see how now we can adjust Model 1 to fit a straight line. And I issued you the question at the end of the last video. Do we have to adjust the parameters of Model 1 in any way, shape or form to fit this straight line data? And you may have realized, or you may not have, that our Model 1 is set up for our classification data, which has 2x input features. Whereas this data, if we go X, train regression, how many input features do we have? If we just get the first sample, there's only one value. Or maybe we get the first 10. There's only one value per, let's remind ourselves, this is input and output shapes, one of the most fundamental things in machine learning and deep learning. And trust me, I still get this wrong all the time, so that's why I'm harping on about it. We have one feature per one label, so we have to adjust our model slightly. We have to change the in features to be 1 instead of 2. The out features can stay the same because we want one number to come out. So what we're going to do is code up a little bit different version of Model 1. So same architecture as Model 1, but using nn.sequential. We're going to do the faster way of coding a model here. Let's create Model 2. And nn.sequential, the only thing that's going to change is the number of input features. So this will be the exact same code as Model 1, and the only difference, as I said, will be features or in features is 1, and then we'll go out features equals 10, so 10 hidden units in the first layer, and of course the second layer, the number of features here has to line up with the out features of the previous layer. This one's going to output 10 features as well. So we're scaling things up from 1 feature to 10 to try and give our model as much of a chance or as many parameters as possible. Of course, we could make this number quite large. We could make it 1,000 features if we want. But there is an upper bound on these things. And I'm going to let you find those in your experience as a machine learning engineer and a data scientist. But for now, we're keeping it nice and small so we can run as many experiments as possible. Beautiful, look at that. We've created a sequential model. What happens with nn.sequential? Data goes in here, passes through this layer, then it passes through this layer, then it passes through this layer. And what happens when it goes through the layer? It triggers the layer's forward method, the internal forward method. In the case of nn.linear, we've seen it. It's got the linear regression formula. So if we go nn.linear, it performs this mathematical operation, the linear transformation. But we've seen that before. Let's keep pushing forward. Let's create a loss and an optimizer. Loss and optimizer. We're going to work through our workflow. So loss function, we have to adjust this slightly. We're going to use the L1 loss because why? We're dealing with a regression problem here rather than a classification problem. And our optimizer, what can we use for our optimizer? How about we bring in just the exact same optimizer, SGD, that we've been using for our classification data. So model 2.params or parameters. I always get a little bit confused. And we'll give it an LR of 0.1 because that's what we've been using so far. This is the params here. So we want our optimizer to optimize our model 2 parameters here with a learning rate of 0.1. The learning rate is what? The amount each parameter will be, or the multiplier that will be applied to each parameter each epoch. So now, let's train the model. Do you think we could do that in this video? I think we can. So we might just train it on the training data set, and then we can evaluate it on the test data set separately. So we'll set up both manual seeds, CUDA, and because we've set our model to the device up here, so it should be on the GPU or whatever device you have active. So set the number of epochs. How many epochs should we set? Well, we set 1,000 before, so we'll keep it at that. Epochs equals 1,000. And now we're getting really good at this sort of stuff here. Let's put our data, put the data on the target device. And I know we've done a lot of the similar steps before, but there's a reason for that. I've kept all these in here because I'd like you to, by the end of this course, is to sort of know all of this stuff off by heart. And even if you don't know it all off by heart, because trust me, I don't, you know where to look. So X-train regression, we're going to send this to device. And then we're going to go Y-train regression. Just a reminder or something to get you to think while we're writing this code. What would happen if we didn't put our data on the same device as a model? We've seen that error come up before, but what happens? Well, I've just kind of given away, haven't you, Daniel? Wow, that was a great question. Our code will error. Oh. Well, don't worry. There's plenty of questions I've been giving you that I haven't given the answer to yet. Device, beautiful. We've got a device agnostic code for the model and for the data. And now let's loop through epochs. So train, we're going to for epoch in range epochs, for an epoch in a range. Do the forward pass. Calculate the loss. So ypred equals model to, this is the forward pass, X-train regression. It's all going to work out hunky-dory because our model and our data are on the same device. Loss equals what? We're going to bring in our loss function. We're going to compare the predictions to Y-train regression, to the Y labels. What do we do next? Optimizer 0 grad. Optimizer.0 grad. We're doing all of this without comments. Look at us go. Loss backward, and what's next? Optimizer step, step, step. And of course, we could do some testing here. Testing. We'll go model2.eval, and then we'll go with torch.inference mode. We'll do the forward pass. We'll create the test predictions equals model2.xtest regression. And then we'll go the test loss equals loss fn on the test predictions and versus the Y test labels. Beautiful. Look at that. We've just done an optimization loop, something we spent a whole hour on before, maybe even longer, in about 10 lines of code. And of course, we could shorten this by making these a function. But we're going to see that later on. I'd rather us give a little bit of practice while this is still a bit fresh. Print out what's happening. Let's print out what's happening. What should we do? So because we're training for 1,000 epochs, I like the idea of printing out something every 100 epochs. That should be about enough of a step. Epoch, what do we got? We'll put in the epoch here with the F string, and then we'll go to loss, which will be loss, and maybe we'll get the first 5 of those, 5 decimal places that is. We don't have an accuracy, do we? Because we're working with regression. And we'll get the test loss out here, and that's going to be 0.5f as well. Beautiful. Have we got any mistakes? I don't think we do. We didn't even run this code cell before. We'll just run these 3 again, see if we got... Look at that! Oh my goodness, is our loss is going down. So that means our model must be learning something. Now, what if we adjusted the learning rate here? I think if we went 0.01 or something, will that do anything? Oh yes, look how low our loss gets on the test data set, but let's confirm that. We've got to make some predictions. Or maybe we should do that in the next video. Yeah, this one's getting too long, but how good's that? We created a straight line data set, and we've created a model to fit it. We set up a loss and an optimizer already, and we put the data on the target device. We trained and we tested, so our model must be learning something, but I'd like you to give a shot at confirming that by using our plot predictions function. So make some predictions with our trained model. Don't forget to turn on inference mode, and we should see some red dots here, fairly close to the green dots on the next plot. Give that a shot. and I'll see you in the next video.